Now that we have a good idea of the Gaussian mixture model, let's see how the expectation maximization framework helps to understand how to estimate a Gaussian mixture model. We're going to say that the generation of a data set that we observe, all of the x values, happens as a generative process based on a particular model. That model could be a Gaussian mixture model where we have parameters theta that indicate the mixture proportions or the likelihood of different values of y, as well as the parameters for each individual Gaussian, that is, the standard deviation and the mean. Model estimation from the data is done through some form of likelihood estimation. So as a first step in our expectation step, we're going to set the latent variables to the values that maximize the likelihood of the data, treating the parameters as observed. That means given the mixture model proportions theta, as well as the parameters mu and sigma squared for each of the Gaussians, we're going to assign each point to a particular Gaussian. In the case of estimating a Gaussian mixture model, the expectation maximization step means that we have the model, which is the prior probability of each of the individual clusters, as well as the parameters for each of the Gaussians, meaning the standard deviation and the mean, sigma squared and mu. In the second M step, or maximization step, what we want to do is set the parameters of the model, re-estimate the prior probability of the clusters as well as the parameters for each of the Gaussians, treating the latent variables or cluster memberships as observed. We're going to iterate this process a number of times until we get to convergence. So this type of algorithm should sound familiar to you because, in fact, that is the idea of k-means. Is this actually k-means then? Yes, it is, but it's a generalization of sorts. So we can think of k-means as having a hard form of expectation maximization, where each individual point is assigned to exactly one cluster. So this makes the cluster assignment discrete. Each point has to belong exactly to one cluster. This discrete form of membership, meaning 1 or 0, makes it difficult to optimize. So what we'd like to do is make it into a probabilistic membership where the cluster assignments are soft or smooth. So how we do that is to add a latent variable z. The z is going to be the latent variable that indicates the cluster membership for each of the m points in our dataset. So we're going to iterate through 1 to m points using the variable j here, and calculate this vector, which is the membership, to all of the clusters. So for example, z1 of j is the probability that point j is associated with cluster 1, all the way to the probability of the point j being associated with cluster capital K. In the E step, since we have the parameters of our model and we regard them as fixed, all we need to do is use the probabilities that we have already established. So for example, we need the prior probability of a point being associated with a particular class, which will be our cluster membership, normalize that over all of the points, and then be able to calculate the labeling of each point basically as taking all of the parameters of our model, our mu and sigma squared for each individual cluster, which would give the probability of that point being generated by a particular cluster, times the probability of that cluster generating that particular point, normalized over the entire set of possibilities. So now we can do the Gaussian mixture model in the case without labels, because we are just pretending that we have these hard assignments replaced by soft assignments, where we have our probabilistic membership of a point to any particular cluster. So we can recalculate the cluster membership prior probabilities, theta k, as well as the mean and standard deviation, just using the probabilistic membership of the point to any of the k clusters. With this, we can get a re-estimation of all the parameters in our model, which are these three variables. And we're back to step 1. This is the case where we have replaced our known labels y, which we are trying to infer, with the expected labels at the particular time step which we're at now. This is the E part of the EM algorithm. So the EM framework works like this, just like in k-means. We're going to first initialize parameters randomly, and while we're not converged, that means that our probabilistic memberships are still shifting by some epsilon amount. We're going to do our E step to weight each example with respect to the latent variables. And in the M step, we're going to set the parameters treating the pseudo-counts that we have actually observed so far as the correct answers at this time step. We're going to do this a number of steps until the pseudo-counts converge and the parameters don't change. So the expectation maximization meta-algorithm can be specialized for different problems. And the easiest case to think about is in the case of Gaussian mixture models, so we've specified it here. This is exactly the same algorithm as in k-means, except we're using probabilistic membership of points to clusters. First, we're going to do our initialization step, where we're going to set our parameters for each of the capital K Gaussians to some random location for the center with some standard deviation, perhaps set to unity, and having a uniform probability of each of the classes. Of course, this initialization step could be changed. It doesn't necessarily have to be this way. And recall that k-means, as well as the EM algorithm for Gaussian mixture models, is a bit sensitive to initialization. Then we're going to repeat until convergence. For each of the points, we need to assign its probability of membership to a particular cluster by computing their expected assignments. We first calculate the probability that is associated with the kth Gaussian. Then after doing that, we're going to normalize so that the distribution of the point to all of the clusters sums to unit distribution. That is our E step. In our M step, we need to re-estimate the model. We do this by going back and asking ourselves what's the correct generative story for all of the points. We're going to do this by re-estimating the cluster centers based on the probabilistic memberships for each of the points. That is, for the prior mixture probability of a cluster, we're going to compute this as the sum of the number of points that are probabilistically associated with this cluster K, and then calculating the mean and standard deviation based on the partial memberships of all of the points weighted by their probability of being associated with that cluster. Again, just like in k-means, we are going to iterate this loop until the probabilistic membership of the points to a class do not change. And we're going to return that as the labeling for our clusters. Here we can see an illustration of how k-means works, which is very similar to what you're going to see in the in-class notebooks and post-class notebook. This is taken from the Wikipedia Commons page, where we see the EM clustering working on Old Faithful eruption data, a geyser in Yellowstone National Park in the US. I'm going to start with a randomly initialized model that you can see has Gaussians of different scales of the axis. And this is just because the different scales of the axis make both of those Gaussians appear quite flat. You can see here there's a unit of 10 difference here and a unit of 1 difference on this axis. Otherwise, they would be spherical. In the first iterations, the model changes substantially, but then converges to the two modes of the geyser. So just like in neural networks, EM is a local optimization function, but actually the likelihood function, as we have hinted before, is not convex. So oftentimes, just like with k-means, we'll need to rerun EM several times with different random initializations and hope for the best. I'm going to pick the parameters that yield the highest likelihood for the models. EM actually goes by a number of other names in other domains. And since I do most of my research in the area of natural language processing, I thought I'd share some of the examples with you. EM is also used in sequence labeling tasks, similar to what is currently used in deep neural architectures for recurrent neural networks. We use the expectation maximization algorithm for estimating the latent labels on sequential models, for example, part-of-speech tags, over a textual sequence. This is basically the underlying algorithm for one of the two major algorithms in hidden Markov models. So, for example, the sentence "time flies like an arrow" can be parsed in several different ways, meaning time is like an arrow, or there's a type of fly called a time fly, and they happen to like arrows. There are several other interpretations that are also possible. Finding the best interpretation can be thought of as a task of assigning part-of-speech tags, like nouns, pronouns, adjectives, and verbs, to each one of these surface text forms. This can be done by expectation maximization, where we say we have observed these individual words, these are our x's, but we want to infer their labels, y's, because we think that their part of speech will dictate the type of things that happen. For example, if I have a determiner like "and," determiners always are followed in English with some type of noun. So it becomes a complex dynamic programming problem, as you can see here, where we've aligned the possible parts of speech to the individual outputs. In the forward-backward algorithm, we use EM in a forward pass where we calculate the alpha I, and a backward pass where we calculate the beta I's, and we try to maximize the joint probability of the labels given a potential parse. A second use of EM in natural language processing goes by the name of inside-out. It uses expectation maximization for tree-like structures like probabilistic context-free grammars. For example, for the same sentence, we would like to decide what type of structure or parse is plausible, given the part-of-speech labels that we had on the left-hand side. So looking at these two interpretations, which one is the analogy, and which one is the case where we have a type of fly called a time fly. Like the forward-backward case, we have a similar structure where we're estimating the structure of the sentence based on a two-stage expectation maximization process. One where we're looking at the outside of the parse tree. For example, if I'm looking at this node, VP, and I'm trying to determine where it's attached, I might look at its external probability, that means how the rest of the sentence relates to this node, as well as the inside probability, or how this node is internally structured, and try to maximize the joint probability there. Variants of EM happen to be quite commonplace and very useful in practice. We have generalized EM, which replaces the M step with a single gradient step that improves the likelihood. We have the Monte Carlo EM that tries to help the expectation step by sampling, which is very important when we have a very large data set where computing the exact estimation probabilities and the normalization step is intractable. We have sparse EM, where we keep an active list of points updated occasionally instead of using the entire E step. It's similar in nature to the Monte Carlo EM. And we have incremental or stepwise EM, which is akin to estimating the parameters of the model based on a small collection of points rather than the entire data set. This is similar to the difference between batch gradient descent, where we use the whole data set to calculate the gradient, versus stochastic gradient descent, where we use either a single point or mini batch stochastic gradient descent, where we use a small set of points. So an important thing to think about is which of these variants are good for what type of scenarios. Please keep this in mind as you study for the test.